Yes. So it looks like I have too much materials, so I go through it and then leave time for discussion and presentation. So this is a continuation of the galaxy formation, and this is the end of the galaxy formation talk. Okay. The advance notice, the question for you is have we already seen population-III star formation and cooling accretion, and why? If no, where is the population-III and cooling accretion? It is quite related to your question. So I will talk many things about the population-III stuff in this lecture. Okay, let's start from the Lyman-alpha escape thing that I talked many times. So again, this diagram shows the Lyman-alpha escape fraction as a function of the color excess or extinction. Well, Lyman-alpha escape fraction is defined by the observed Lyman-alpha divided by the intrinsic Lyman-alpha estimated from the H-alpha or UV luminosities. So this is just I let you know it again. So this is the it is known that there is the anti-correlation between the Lyman-alpha escape fraction and the color excess, and this relation is known since the 1990s. And of course, the higher extinction value have the less Lyman-alpha escape. And the interesting thing is that if you measure the Lyman-alpha escape fraction as a function of the color excess, Lyman-alpha emitters are falling in around here. So if you compare this relation of the Lyman break galaxies shown with the red line, this comes beyond the Lyman break galaxy relation. And some of the Lyman-alpha emitters may show the extremely strong or large Lyman-alpha escape fraction. And Stephen Finkelstein introduced the Q parameter several years ago, and the Q parameter definition is the optical depth of the Lyman-alpha divided by the continuum optical depth at 1216 angstrom. So then, if the Lyman-alpha extinction is the same as the continuum, then the Q should be unity. But if you have more Lyman-alpha emission line, then you have the less than unity. So this dashed line shows the changing the Q values. So here is the unity of the Q. So maybe it has a large scatter, but some of the sources the distribution is skewed to somewhere toward the smaller value of the Q. So there's a possibility that Lyman-alpha optical depth would be smaller than the continuum optical depth. So to explain this, so many people asked me a question: clumpy, media. Where is the clumpy media? Finally, I talk about it. Yes, Neufeld effect. Yes, this is very famous, and I think many of you know. Well, Neufeld says, if the ISM is confined in the clumpy clouds, then if you have the source of the Lyman-alpha, then it travels through through the media and scattered on the surfaces of the clumpy clouds. On the other hand, the continuum should go through with no resonance scattering, so you have more extinction in the continuum, and Lyman-alpha emission lines are traveling through the dust-free regime. So you have more Lyman-alpha than the UV continuum. So this is the idea, and people bring this and to explain high equivalent width of the Lyman-alpha. And in the past few years, now they are having the great advantage of the calculation power of the simulations. People carried out realistic. People made the realistic models of the clumpy ISM medium. So there are two efforts, two studies. One is using the radiative transfer models and having the clumpy cloud media, and having the radiative transfer modeling, and using the very sophisticated adaptive mesh refinement technique, and to look at how the Neufeld effect works. And also the another effort is made by the Diva, and having the more realistic distribution of the homogeneous, smooth distribution of the ISM, and plus the clumpy media. So two of these simulations suggest that, yes, Neufeld model exists. So this right panel shows the escape fraction of the Lyman-alpha divided by the UV continuum escape fraction. So this is a 1, so unity. So beyond 1, so Lyman-alpha have the excessive escape. And their claim is that, yes, the Neufeld effect exists because there's a regime, there's a parameter, there are some results showing the excessive Lyman-alpha escape in these clumpy media. However, they also claim that Neufeld effect doesn't take place in the realistic interstellar medium of Lyman-alpha emitters, because as you can see, this is this fraction as a function of the color excess. This is the B minus V of the 0.3. As I said, for the Lyman-alpha emitters, color excess is the near to unity or less than 0.1 or so. So in other words, most of the other Lyman-alpha emitters are residing in this regime. So in other words, less Lyman-alpha escape fraction is expected in the model. And so they say, to realize Neufeld model, you need the quite static ISM, outflow velocity is very low, and very dusty component, and also they should be very clumpy, like with the contrast of the 10 to the 7th. So in other words, most of the gas is locked up in clumps. So it sounds very unrealistic. So so the bottom line is that Neufeld effects exist, but this is not the major reason to explain the high equivalent width of Lyman-alpha emitters. I think this is the general agreement in this field, but I'm not sure. But let's discuss. Okay. And now I talked about the modeling of the Lyman-alpha emission line. So let me touch the famous expanding shell model. Probably some of you are working on this model. So, the expanding shell model is a very interesting model. The model structure is the shell of the gas and dust, and which is expanding and expanding. So this model is justified by the nearby starburst galaxies, which shows the galaxy scale super shells made by the supernovae, multiple supernovae in the star forming regions. So you are modeling such a super shell with the expanding shell model, and there are 4 major parameters for this expanding shell model. One is the Coulomb density, neutral hydrogen Coulomb density (NH1), and outflow velocity of Vout, and Doppler velocity within the gas in random motion within the shell, and the optical depth of the dust extinction within this shell. Okay, so having this expanding shell model, you can explain the many varieties of observed Lyman-alpha emission line profiles. These are 3 representative line profiles of observed Lyman-alpha emission line fitted with expanding shell model. And the left one is shows the asymmetric Lyman-alpha line with the red wing. And the middle one is has the weak blue peak. And the right one has the double peak. And this black lines are data, and the blue lines are best fit shell models. So it explains very well. so then you may think that how it works. So let me explain some ideas of the line profile. So well, again, this is the model structure, and there's a Lyman-alpha source. And there are three major components: no backscatter, one backscatter, and multiple backscatters. And for no backscatter component to the observer is that you have Lyman-alpha emission line and you have the expanding shell. So some of the blue components are scattered in this line of sight, but are still scattered. So you do not find this, but still major component of the Lyman-alpha survive. So you can observe such a no backscatter component, which shows the very small velocity offset. And the second component is one backscatter component. So you have the expanding shell. So the Lyman-alpha photons traveling to this direction, then the red shifted Lyman-alpha photons are scattered by this media, and then it is the scattered out. So this media is receding by outflow velocity. So the observed one backscattered light is more or less 1 to 2, about 2 outflow velocity, 2 times the outflow velocity. So, and also multiple scatter component has the even more red shifted. So, and the interesting feature of this model is that if you have the high neutral hydrogen column density, then you have more backscattered light. So in other words, you have more red-shifted component, like the velocity offset of the Lyman-alpha is about twice as the outflow velocity. And if you have the small neutral hydrogen column density, then you have more direct component or no backscatter component. So you have small velocity offset of the Lyman-alpha between the velocity offset between the systemic velocity and Lyman-alpha. So well, this changes about 10 to the 20 per square centimeter for the neutral hydrogen column density. So now the key components is this Lyman-alpha velocity shift from the systemic and also the outflow velocity. So what the recent observations tell? Well, recent observations see the absorption lines of the silicon, carbon, low ionization lines in the UV spectra as shown here. So these are magnified such a low ionization metal absorption lines. And this is the zero velocity, systemic velocity of the Lyman-alpha emitters determined with the H-alpha lines. And as you can see, the metal lines, low ionization lines are blue shifted. And typically it's blue shifted by the 200 kilometer. And here, this red one is the stacked spectra, continua of Lyman-alpha emitters. And as you can see, the blue one is the stacked spectra of the Lyman break galaxies. Of course, Lyman-alpha emitters show the less metal absorption lines because probably less metallicity. But well, the velocity shift is pretty similar, and in fact, the outflow velocity from the Lyman break galaxy spectra suggested by the Lyman break galaxy spectra is about 200 kilometers per second. So Lyman-alpha emitters and the Lyman break galaxies have the similar outflow velocity that is suggested by the absorption lines. And then the second component, important component, is the velocity shift of Lyman-alpha. Well, this shows the H-alpha luminosity for the systemic, and the blue line is the Lyman-alpha flux, Lyman-alpha line. So as you can see, the typical velocity shift is as small as about 200 kilometers per second. If you plot the velocity shift of the typical Lyman break galaxies, it comes around here. So obviously, the velocity shift, Lyman-alpha velocity shift of Lyman-alpha emitters are significantly smaller than the Lyman break galaxies. So Lyman break galaxies have the 400 km per second, but Lyman-alpha emitters are about 200 km per second. As I said, outflow velocity is 200 km per second for both populations. So Lyman-alpha emitters have the very similar outflow velocity and Lyman-alpha velocity offset. On the other hand, Lyman break galaxies have the about twice larger velocity, Lyman-alpha velocity offset. So, well, if you remember this relation, so neutral hydrogen column density is large, then you expect this number, but it's pretty similar to the Lyman break galaxy case. But on the other hand, Lyman-alpha emitters have the small Lyman-alpha velocity offset. In other words, you have more direct, no backscattering light or photons. And so in other words, column density of the neutral hydrogen would be smaller for Lyman-alpha emitters than for Lyman break galaxies. And well, to conclude the Lyman-alpha escape fraction, I want to finish with this plot. Well, again, so this is the evolution of the Lyman-alpha escape fraction, and it's increasing from relative 0 to 6 or so. And how you can interpret this, so physical reason. So I left this issue yesterday, but I want to discuss more detail. So again, this is the same Lyman-alpha escape fraction as a function of the redshift, different version, but with many different information. So, well, to explain this, there are 6 possible reasons of the Lyman-alpha escape fraction evolution. One is the IgM absorption. Well, towards high Z, you have more Ig absorption. So, in other words, you have less, Lyman-alpha emission lines expected for the observations. However, it is totally opposite sense. For high Z galaxies, you observe less. You observe less Lyman-alpha emission line. But well, if you correct, IgM effect, absorption effect, you have more, efficient Lyman-alpha escape. In fact, so well, if you correct this effect, then this open squares are the corrected value. So even this strengthens the Lyman-alpha escape fraction evolution. So the second possibility is the stellar populations, but as I said yesterday, the Lyman-alpha emitters do not show the significant evolution in the stellar population. And outflow velocity, as we saw that at redshift around 2, the outflow velocity is 200 km per second, and also the recent Keck results suggest that at redshift 4 to 6, the outflow velocity is as low as the 100 to 200 km per second. So it doesn't show the significant evolution signatures, although the still numbers of the galaxies measured are limited. And the next possibility is the Neufeld effect, but well, this is ruled out because this is realized only in the special case. And the fifth possibility is the dust extinction evolution, but well, color excess doesn't change much from, say, redshift around 2 to 6. And if you, correct the effect of the dust extinction, assuming Q equal 1, or in other words, Lyman-alpha extinction is the same as the UV continuum extinction, you get this. So this still has the trend of the increasing escape fraction. So this doesn't explain the increase of escape fraction. So the last thing, the last remaining thing is H1 gas evolution. So if you have less neutral hydrogen, and then you have less Lyman-alpha scattering or absorption. So you can expect the more efficient escape of the Lyman-alpha. So having this motivation and having the other expanding shell model to explain this relation with the change of the neutral hydrogen column density, you can get this. So this shows the evolution of the column density from redshift to 0 to 6. Although there are large error bars or uncertainties, but at least you can say if this escape fraction is totally made by the H1 gas evolution, then neutral hydrogen column density decreases by an order of magnitude from redshift 0 to 6. Okay, so yeah, the last topic, the population 3 thing, I think many of you are interested in. And okay, so well, Lyman-alpha emitters are famous for population 3 because it shows the extremely high Lyman-alpha emission lines, like equivalent width is the greater than 240 angstrom. So this value cannot, this large value cannot be explained by the ordinary solar metallicity salpeter IMF. So this was recognized since 2002 by the Malfton and Rose, and such a population exists about 10 to 30% of the Lyman-alpha emitters obtained. And to explain these large, Lyman-alpha equivalent with objects, there are 3 major suggestions. One is the Neufeld effect, and the second one is the cooling radiation, and the third one is the population 3. And as I said, Neufeld effect may not work for the realistic case, and also cooling radiation, I have already touched it. So then here I want to discuss more about population 3. So according to the Daniel Chalet's model, of course, you have, for population 3, you have very massive stars, metal-poor stars, metal-free stars, so that produce a lot of ionizing photons and producing the large equivalent Lyman-alpha equivalent width. For example, for the population 3 burst, with age below 2 mega-year, that gives the hundreds to 1,000th of the Lyman-alpha equivalent width. And another important feature of the population 3 is helium-2, as you know. Such a young massive stars produce the very hard ionizing photons exceeding 54 electron volt, and that allows you that makes the helium plus ionized and giving the helium-2 emission lines. And this shows the predictions of the helium-2 equivalent width as a function of the starburst age, and such a population 3 can accomplish the very high helium-2 equivalent width up to 100 angstrom. So combining these features, you can probe the population 3. And there are 2 claims of the helium-2 detection, helium-2 1640 line detection. So this is the first example, first one of such a helium-2 line detection. This is the PLG1 identified in the NOAO deep and wide survey field, and this was first. This was identified as a Lyman-alpha blob at redshift 2, showing the strong Lyman-alpha emission line, and the subsequent spectroscopy given by Morris-Prescott et al. Shows the strong helium-2 emission here. But interestingly, there are no carbon-3 and carbon-4. So, and they place the upper limits of such a carbon emissions, and looks like, looks like the weak, metal lines. So this was the very strong, the candidate of the population 3. But the subsequent deeper spectroscopy show the significant detection of the carbon-3 and carbon-4. So now the other people understand this object is not population 3, but heated by AGN. And the second example is, as you know, the recent claim of the recent discovery of the CR7 at redshift 6.6. And this shows, again, strong helium-2 emission line. And the equivalent width is very high, 80 plus minus 20 angstrom. And this is the ratio of the helium-2 to Lyman-alpha. These values of a helium-2 emission line is about twice as high as the object of press PLG1. And no metal lines are detected so far, having the upper limits. However, still this upper limit is not strong enough. And there are three continuum components, and SED fit indicates that maybe this A component is pretty young and possible young population. And yes, okay. So, and I will discuss more about this object in the comparison of theoretical models. And what about the average Lyman-alpha emitters? Well, you have no helium-2 detections, even you stack. So you can place the upper limits of the helium-2 emission line for redshift 3 to 5 of this. So there are no significant detection of the helium-2. And here, I think this diagram is quite powerful to diagnose the population 3. The y-axis is the spectral hardness defined by the numbers of the helium plus ionizing photon divided by the number of the hydrogen ionizing photon. So in other words, how much very energetic photons over 54 electron volt exist compared with the 13.6 electron volt photons, and you can estimate the the spectral hardness using the helium-2 and Lyman-alpha emission line. Then from the stacking analysis, these are just giving the upper limits and ruling out the possibility of the top-heavy IMF thing for the ordinary Lyman-alpha emitters. And if you plot the PLG1 and CL7, they are placed around here. So compared with the population 3 and the top-heavy extreme population 3, it goes very high. And so, well, if this is true, then you cannot explain these objects as the population 3. However, there's a caveat. So if you use the Lyman-alpha luminosity, then as you know, Lyman-alpha luminosity has the correction factor of the escape fraction. So if you correct the escape fraction of the average value of the 0.2 for redshift around 7, then these points comes down around here. So then probably you can factor of 0.04 or something around here. So then it's very close to the population 3, but still it's a little bit high. So well, I think it is very interesting that to measure not the Lyman-alpha emission line, but some other Balmer lines like H-alpha or H-beta for this particular object to derive the more accurate spectral hardness. And also another important thing is to look at look for the deeper spectroscopy and to check whether there exist metal lines. So this is the summary of the galaxy formation 3. So I talked about the three topics. One is the extended Lyman-alpha halo, and the bottom line is that extended Lyman-alpha halo and Lyman-alpha escape mechanism, and the other population 3. So time is running out, so I would like to move on to the discussion and presentation section. So again, the question here is have we already seen population 3 star formation and cooling accretion, and why? And if no, where is the pop 3 and accretion, cold accretion, and how you can identify them with today's technology. So please go ahead for discussing. any question is fine, including this presentation 5 thing or 4 thing that we did. So either way, it's fine. Population 3, code acquisition, or the urgent issue of the Lyman-alpha emitter observations. Okay? Any volunteers? Yes, thank you. Please use the microphone. Otherwise, okay. It's not recorded.
Okay. Hi, I'm Saurabh. I'm from University of Minnesota. So we talked about like both the questions, the previous one and this one. So for this one, like we came up with an idea, like we need to observe something in near infrared, and like population 3 stars are supposed to be towards the higher redshifts, like somewhere, let's say 6 to 7. If you probe around that, then you will be like at the edge of near infrared regions. So in between near infrared to far infrared, and that's where you will observe population 3 stars. And for those, like we expect like very narrow helium-2 lines, and we should not have metal lines like which we talked about, like carbon and silicon lines. So, and like we expect that this will be by the next generation JWST. I think we can do those observations. Yeah, that's it. Yeah.
Sorry, I missed something. So, in what way JWST helps? Can you clarify it?
The wavelength range.
The wavelength range. I mean, the wavelength range we talked about.
Optical emission. So,
Redshifted.
redshift.
Yeah.
High Z.
Yeah.
Yeah.
Okay. But you know, the populations with starburst phase is very short. Like as I said, 1 mega year or 2 mega years.
Okay.
So you need substantially large survey goal
Okay.
to search for such a very young on-site.
Okay.
So I don't know how.
So we came up with
large, survey can accomplish the large survey. I'm just asking the question.
Okay, so like we came up with an idea of constraining like the regions like on the redshifts where you can observe the population 3 stars. I mean, let's say we talk about reionization, and we at different redshifts, you know how much the universe is ionized, and say that in reionization is driven by the population 3 stars. And then from there, like if you know the ionization state of the universe at different stages, from there like back calculate how many population 3 stars you should have to have that reionization. So from that back calculation, you can get to know, okay, like we should observe so many. In this redshift, we'll have a lot of population 3 stars. Then you can probe in around that redshift and get to know more population 3. I mean, that's what.
Any questions? So what's your name again?
Saurabh.
Saurabh.
Yeah.
Any questions you have? Okay, yeah, thank you. So actually, we have 2 more minutes. So let's have the other, ideas. So anyone who can volunteer? Maybe I think there was some active discussion around here, but did you discuss something? No? Just chatting?
Number 4.
Okay, please.
Thanks. Okay, so I don't want to be too loud. So if we go back to question 4, question 4 is my thesis and near and dear to my heart. So, I mean, some of my thoughts on this are that the LAES, particularly in light of these emission line galaxy surveys that are happening in the next, well, with HETDEX, Euclid, these other things, I think we need to understand why does Lyman-alpha escape from some star-forming galaxies and not others? And is this a factor of physical or morphological properties, or is it just sort of random selection effects as some function of mass? Because if Lyman-alpha comes out and is biased towards particular types of galaxies, that provides, it makes it really difficult for us to use LAEs as general star-forming galaxies. But if it just turns out that Lyman-alpha is escaping on some sort of random collection of sightlines, then we can use galaxies from HETDEX, from Hypersea PrimeCam surveys and others to just trace the general star-forming galaxy population, which would be, I think, incredibly powerful for galaxy formation as these select low-mass galaxies that we can't find really in any other way across such wide ranges.
No, sir. Do you have any results on what it actually is?
So I guess the question is, do we have results on what it is? That depends on who you ask and at what redshift you work. So it's really hard to find comparison samples for LAES at high redshift because classically we've always looked at Lyman break galaxies and sort of the alphabet soup, BZKs and other things, and that they have mass differences by like a dex. And so obviously things are going to be different. And so I think some of the optical emission line galaxies from 3D-HST seem like good examples. And as Euclid, well, whenever Euclid happens in like, what, 5 or 10 years? I don't know what the timeline is on that. And W first, when you have H-alpha galaxies, emission line galaxies selected across wide redshift range, then I think that will help.
Okay, thank you, Alex and folks. So it's time. So I would like to conclude the galaxy formation sections. So I will switch let's switch the speaker.